Yeah. My name's Ken Murphy, and I'm Director of the Future Industries Institute here at the University of South Australia. This feels like one of the most normal things I've done, I reckon, about the last 15 months, to stand here in front of a group of people from all over the country tonight. This was just telling me we even let him in through the airport this afternoon without too much scrutiny, so welcome. First of all, the owners of the traditional land on whose land we gather tonight. We acknowledge the deep feelings of attachment and relationship with Ghana people to the country, and we respect and value their past, present, and ongoing connection to the land and its culture and beliefs. Now, I get to tell you briefly about the Future Industries Institute, just very briefly. So, the Future Industries Institute was about 6 years ago, and combination of three previous institutes that existed here at the university. And what we do is we tackle challenges that are relevant to society, particularly to industry, and we look at delivering outcomes to the benefit of the real world. And many of the staff in the institute, including myself, have worked in private industry. So we have to break the mould of the traditional research institute within the university, in the sense that several of us indeed have experience across quite a wide range of industry sectors. This institute has just over 200 staff and students, a research income of around about $20 million a year, and that's from the very fundamental through to the very applied. I guess in terms of the very applied, I mean, I'm just thinking back to something I did about half an hour ago. Some of our researchers here are involved in the MINEX CRC. And we've just spent $750,000 on a new truck with the Colin tube drilling rig on. And we're about to drill a 1,000 metre deep hole about 600 metres from here, or probably less, 300 metres from here, over on the far north eastern corner of the campus. So we really do the applied side of things. Tonight, I'd like to launch this as a joint event of several professional organisations, that includes Materials Australia, Weld Australia, and the Australian Corrosion Association. This is all under the umbrella of the ITTC, the Surface Engineering for Advanced Materials, otherwise known as SEAM. And I had the privilege, Chris and I couldn't quite work out how long ago it was, a couple of years ago, I think, roughly. I attended the opening of SEAM in Melbourne. So time flies. So tonight I'd like to acknowledge Chris Byrne, the Director of SEAM, who's here with us. He will speak shortly after me. And also our speakers from outside the university. I've got Thomas from Schläfer sitting here from LaserBond, and Dr. Paul Colegrove from AML 3D. And both these companies are great examples of local SMEs, small and medium enterprises. They're absolutely full the backbone of the industry in our state, and really much of Australia. They're innovative, they deliver solutions for industry. LaserBond, of course, works in the area of providing cladding for wearing systems for various parts, for various industry sectors, particularly mining. At AML 3D does wire arc welding as an additive manufacturing technique. And I'm going to hear a little bit about that from both of the speakers tonight. So look, that's probably about all I need to cover. I'm going to hand over to Chris now to talk to you. On the park side, it's a board meeting to go to. I'm going to be up at the Leader, which is about an hour and a half drive away, and it's in the traffic that we have on our track roads still that way. So I'm about to depart. But I hope you have a great evening. I hope you've enjoyed what you've seen. And thank you for coming and taking part tonight. So thank you. Do I need a mic? Yes. This is for who?
No. We're also online on Zoom, so for that you're going to need that, Chris, unfortunately.
I feel like a movie star. I never thought I'd have to pull on a jumper to come to to Adelaide. What's happening to the weather here? I am actually an Adelaide boy. I did go to the SAIT, South Association Technology. I did attend this campus when you had to wear rubber boots to get through the mud, and when you didn't have to take the parking.
So I'm familiar with the campus and with Adelaide a little bit, although all these newfangled roads sort of mix me up a little bit. So SEAM, Service Engineering for Advanced Materials, is part of the Industrial Training, Transformation Training Centre, sponsored by the ARC. Please write down all of those acronyms for your exam later on. So, what does SEAM do? First of all, we do have funding, approximately $10 million in cash over 5 years, $2 million a year, $1 million from the federal government, the ARC, $500,000 per year from the university nodes, Swinburne, UniSA, and RMIT University. And then the other $500,000 comes from industry. So there are 13 industrial participants within SEAM, of which several are represented at UniSA. So we've got LaserBond, for example. Now, industrial training, what does that mean? What that means is that we're supporting early career researchers, postdocs and postgrads, 25 postgrads and 7 postdocs. So we are supporting, we are supporting 30 or so people for the future. That's who we are working for as academics and industrialists. So when we had the meeting at Swinburne a few weeks ago, I was looking around the people, all of these young faces, and I said, crikey, I really hope we're doing some good here, right? Because these people will be advancing manufacturing for Oz into the far, far future. That is the aim. We are working for these young faces. When we're writing these proposals, Colin, Christy, Nikki, when we're sweating it out, when we're trying to schmooze some money off our industrial people, we're working for the young people. So that's industrial training, because there's embedment of the young people within industry. So that when they finish their degree, or when they choose that you cannot live on postdocs forever and ever, amen, they will go into industry and be of direct benefit from week 1. That is why I'm here. I'm here to promote SEAM, and also I'm going to pass the hat around a little while. On fishing for new projects. We, SEAM, is fishing for new projects so that we still exist in 20 years. So the young early career researchers are carrying out relevant research. So if you do wish to carry out a project on surface engineering, and surfacing is the face of matter, look at me, right? Surfacing is the face of matter. Everything revolves around surfaces. Then approach someone here and you'll have a very good applied R&D project. So I've talked about why I'm here, I've talked about money, I've talked about industrial training, I've talked about reflections, supporting young people so they can be relevant to industry. And now I really must sincerely thank the USA Loan, Colin, Nikki, Christy. Thank you very much for being part of SEAM and flying the flag. It's important that we recognise the professional societies and industry. I'll be here all evening, and please approach someone. Talk about a grain boundary. Say something about a grain boundary, about metallurgy, or fracture. And I think that'd be really exciting because that will lead to a project. Please don't talk about management. Talk about something about science and technology. And now I'll hand the mic back to Madam Chair. Thank you very much.
Thank you, everybody. Thank you, Chris. Yeah, indeed, I'm very glad indeed that you could make your way over from Victoria, South Australia, and even that the borders in the were kept open just for you.
Thank you.
Take our first speaker for tonight is Thomas Schläfer from LaserBond. Thomas is engineering manner, research and development at LaserBond for almost 4 years now. And yeah, LaserBond is a surface engineering company. We just around the corner really. It's like we live in a kilometer from here. And they do laser cladding and thermal spraying for remanufacturing, but also to coat new parts so that they last longer. They also sell turnkey systems, so if you want to have a laser cladding or thermal spray stuff, you can get that from them. And without further ado, please.
Ladies and gentlemen, welcome to my talk. I hope you don't have to stop me when I add some slides. Please stop me if I get too boring. Welcome to my talk. In the next 20-30 minutes, I will bring you about the house, and that's the problem spraying process, spraying processes as well as the laser process. But first of all, just a brief company, LaserBond, nearly 30 years old. We started in 1992 as HVOF Australia, then introducing HVOF demonstrate technology to the Australian market. Relatively early, many companies actually worldwide working with other deposit processes. And this is decided to invest all their money in cladding processes. So since 2001, actually during one of the companies worldwide, we utilized focused laser light for deposit cladding. Since 2007, we are listed on the ASX. So if someone's interested in buying some shares, please have a look. At the moment, staff, in facilities. The company was founded in New South Wales. Where we still have our headquarters in Sydney Lane. Also, we set up a facility in about 2 kilometers down the road from here. And last year we acquired USP in Victoria. So now this is trying to moment we serve all the Australian and some of the world market. So we see ourselves as a service engineering company that develop our service engineering technologies, applications, over the time also the turnkey solutions. So separated from the slide, actually it's working hand. The divisions basically focus on the coating and cladding services. On the left-hand side, services, that's mainly the information of new parts. This doesn't contain only the coating process or cladding process, but also the post machining. Also the pre and post machining. And on the right-hand side, similar words only for taking serious things. And then for an area of technology that provides the development of systems, and for all our systems are the program. And last of all, the smallest, but on top, of course, the research and development, where we call it very young analysis. We develop processes, investigating materials, and the possible. So why do we need coatings overall? I mean, typically when components are being designed, people more focus on the structural integrity of the part they design. So here we look at mechanical parameters, trimming hardness, treatment processes, the material here for the structure. So I
think Chris said it all revolves around the surface. That's absolutely right. Because we say that in many applications we've got a totally different load, totally different demands of the electrical. So the solution could be material that can be low, chemical properties, and the biological or chemical but then on the parts of production process can be complicated and parts in so the idea of basically is to combine the super material for the structural integrity of the part and apply coating that protects the part against environmental. Okay. Or also biological so basically the entire process consists of looking at the operating environment. When the process of coatings development is we've got the three major factors. We have the operating and environmental based on these. That's here we are. Breaking corrosion, corrosion effects, pickup pressures, different acids. So it can be a very complex load collector. Based on this, we choose surfacing material and, of course, suitable application framework. But also, out to these two, also the piece material, the actual substance material has to be considered. So I just want to highlight two. Here just listed what we have in house. We focus on thermal spraying. I mentioned the typical mixerization process, plasma spraying, but mostly high velocity oxy-fuel, HVOF spraying. We are in laser cladding. We at the moment utilize 4 laser cladding systems. So that we use Fronius and have 2 products called nano and microclips. Last but not least, with the acquisition of UST, LaserBond Victoria, we now have also plasma transfer arc welding mounts. So just basically the spray process. It's a line side coating process, and we typically work with metallic and similar materials. We've got a feedstock material which can be either powder, can be wire, can be a suspension, it can be a water, and even different more. And these materials are in order to heat up, in some cases atomize it, and then the pellet was the surface. Regarding the thermal energy of the energy, that can be generated by means of an electric arc, electric discharge, different types of combustion processes, or just an electrically preheated gas. This is then called cold spray, despite we see gas temperatures in the range of 5 go to the one later. Typically, these processes are very universal. Basically, any kind of material with a longer melting point and the other material, very versatile, thicknesses. These processes can utilize again to apply polymers up to oxide ceramics or refractory metals. Substrate materials, as I said, basically everything's possible. Just a quick look at what's happening at the surface. So we have the impinging melted, the semi-melted particles, a certain also depending on the process, there are between 100 meters per second and 700 meters per second plus. That depends on the process. The temperatures also vary. So this melted or semi-melted particle pitches on the surface, flattens, builds the undercuts. So we need a rough surface here. Builds the undercut, and then we have a mechanical interlocking between the particles and then the coating is built up by millions and millions of these single particles. Just to give you some visuals of the processes, I mentioned the top left, the wire art spraying or metallization. It's a relatively simple process, but still very useful for many applications. It also based just feeding two electrically conductive wires to mark the market between them. The electric arc is melts the tip at the surface. And also use the electric energy to dissociate the iron gases, basically. After the dissociation and ionization, gas into the electric arc, we combine and then set to some other heat. Theoretically, in the range of 10 to 15,000 Kelvin. So this also makes it suitable for we work most with is the high velocity oxygen feed process. Here we have to provide the kinetic energy combustion process, which is used in the back of the line. Basically, and then get a steady line. Velocity because we need to this waste gas to affect the power market. And accelerate them this case to something like 750 meters per second. The other system can measure these different parameters to the material as well as the kinetic energy, have a tremendous influence on the products. So on the left hand side is the after melting, the part stays relatively cool with both parts. And so we try to keep the surface temperature below 200 degrees C. We say what I mentioned, the lamellas or splats here, the arc spray coating, the grayish. So here is some oxide stringers. So some porosity, some oxide stringers, but it's a very reliable process. For example, this kind of coating, if you buy a Porsche four-cylinder engine box coated, it's very cheap, very easy, but it works. It works fantastically. Well, it works better than great cast iron for this application. And on the right-hand side, we see an HVOF coating, high kinetic, low thermal energy. So here you can see we've got about the same magnification, very extremely dense coating. some applications for HVOF, instant outer turbines, landing gear, platform replacement, robots in chemical industry, amongst many, many others. This is the laser cladding process. We use, first of all, we still use the word laser cladding. If you Google it, there are other words that do more hits, but we were using it for 20 years. So if you look at the very bottom, you find laser metal deposition, direct laser deposition, direct metal deposition, direct energy deposition. They basically all mean the same difference. So we go to the original one. So it's laser cladding. It is, to some extent, deposit well process, focused laser light as an energy source. So here we have a schematic. I stole that from Andre. Sorry for that. But your graphic was better than ours. So with this process, we focus laser light. We nowadays we started with carbon dioxide lasers, 10,000 nanometers. Now, typically, diode lasers are being employed. We focus the laser light onto the so-called spot. A melt creates a melt pool. Of course, and we have the relative diversity between the laser beam. Basically, heat up 90 try to melt the surface as little as possible. Then inject the surfacing material into that melt. In a nutshell, the big advantage is you can produce very thick claddings. So compared to thermal sprayers, then maximum half a millimeter, you can do actually something up into the range of 12 millimeters. The biggest advantage for me is to have a bonding between the cladding. So no mechanical interlocking, it's in the no connected process, which is when we go back to the first one, we try to shield up our part of an environment. No interconnected porosity, very little health penetration, very little efficiency. That means that our process most of it actually stays on the part. Then, for example, the Fronius rate process sometimes only half of it stays. But therefore, don't stay. And due to the weather, the laser beam can be controlled very well controlled. So it can be used to welding materials that are just about overkill or laser free systems, so then compression that's required. We typically use 6-axis robots to manipulate the laser pattern optics and the powder nozzle. This is also 5 gases, powders, and the optical fiber. Guide the robot. And then we have to set up also a filtering table, tail slot, and the 6-axis robot in this case. Version that's on laser 5 we have installed here in Additive. Picture the parts, just quickly cross-section for the laser cladding. Remember I mentioned that we talk about dimension, wide penetration, just giving an impression. We see a steroid 21 cobalt and cladding cobalt 20 molybdenum on a G250 substrate, so it's not like steel. And this is the interface. Hard to see on the picture. Now, hard to see on this picture, but you have to really take some gas pictures. Here for the island, you can see that the part in my island migrates into the cladding, so very little dilution. At the bottom, the other way around, you see no cobalt migrating into the base material. So this is something like you might be. That's the picture of the white set. This is an iron-based alloy with narrowly precipitated special carbides, beautiful 1463 Rockwell factory, and very nice, very fine carbides. What are workforce on so-called metal matrix composite claddings. So basically, not scaled up metal. Unfortunately, you can't do the carbide content, they can do the hard metal, but we still can go up to something like 68 or 70% in some cases. So what is in place in the actual cladding is a metallic binder, and the brighter points, that's the carbides, really only distributed here in the cladding. So with this, just with the binder and carbides, we have a lot more to play around. We can use different binders, harder, softer, more corrosion resistant, less corrosion resistant. Then we even can play around with the carbides, carbide size, carbide types. So the advantage is I can tailor the matrix to maybe to combat impact. Or I can tailor it towards corrosion resistance. I just briefly some other welding processes. This is a spiral WA process. You can see weld penetration. Last penetration here. Also the PTA process, like rely on arc, and the arc is a bit unstable, much more unstable. And on the left hand side, there's a close padding. Over whatever carbide, which is at speed. And just to go over comparing the two, nutshell, laser cladding, you can imagine that's a big advantage when it comes to networks. Thermal spraying just in time, which gives us the possibility to code basically any time. Laser cladding typically on metallic substrates always need metal in there. All the thicknesses therefore much thicker, so we can provide much higher we demonstrate that it's a relative thin. Gas type coating, gas type coatings, demonstrate the current metal composites with sitting. Paper cladding, we have some it's smaller than a 10 hour lighting process, but it's still there. On the other hand, the thermal spraying just the same blocking, same magnification, both metal matrix composite coatings, laser cladding, big carbides, about 25 microns plus. So, structure. Just very quickly, the materials we work on a daily basis with, and that give us the big leeway we have when it comes to tailoring coating solutions. We do lots of wear testing within public projects, mostly here at the University of Australia, Colin at the scheme. So we just have simply seen today the latest can tester, the public tester, very interesting device. But typically the G65, G76, G99. Just quickly some files from a previous project and some previous projects where adding project to standard materials. Well, here you see the pin on this tester. On the left hand side of the y-axis, the wear rate, and lots of different materials. We use a good lot of 100 conductance, hard cold. We have that's a hard mathematics laser cladding. You can see how much smaller the wear rates are. And similar erosion is a lot under about 10 times. 5 times the wear by X31. Strictly dry erosion. Platform replacement is one of the big subjects we're working on. Platform replacement is a big need for this in Europe. It's very hard to set up new facilities. Platform companies there get extra. I think they have extended this licenses for another 7 years. But all the companies are looking for alternatives. So it can be done with both processes. We're currently working on iron-based alloys, which won't outperform this largely costly material, but will become very close and will outperform hardcore. And of course, we do the laser also. Iron-based material. Just the workshop, basis, repair of holes and sharps, let's say, costly parts, parts we refurbish are coming from overseas, and they have to be scrapped just because some of these parts that was done in Callan, just bring them down the road, get them back, and tailor the coating. And that's something that's why we started with going towards. I call it feature in this case, so doing that. Just briefly, the part here, small and deeper. We have so beside the seat for the line switch, we're working on project now. Beside these 2 projects, we can see in our project together with NSI and LSC Research. Industrial sectors, we work with lots of mining processing and supplies in Australia, heavy industries, construction, manufacturing, energy, and hopefully some more in the future. That's a good one. Thank you very much for your time. Maybe can I cover? Do I get a question or not?
Yeah.
That's really it. Thank you very much.
Yeah, having a lecture on the first grade and again, starting to have really industrial applications that many of you may have seen before, and maybe you see where you can apply this technology. Do we have any questions from you?
Well, there's potentially a sensitive question that we might wish to ask. Relative costs of laser cladding versus HVOF. So relative costs in terms of the initial kit, the initial equipment, relative costs with regards to the initial feedstock. I'm not asking for numbers, just making assumptions. And relative costs with regards to operation. Consumables and operation. Any ideas, any ballpark figures for us?
I should have answered the question, which part, how many parts, which part, which materials. It's process machine is required, process machine is required, some area of the entire house that can be done for single part or single application. In hardcore, just give the whole
We're not going to take it from relative to macro. If you also relative to the bottom thick.
including finance. That's it. Laser planning typically has you're working on electric load, which minimize the cost machinery. When what control what's the load upgrade they have, 0.01 per hour. So, microns per hour. We do something like, but the mathematics of the other materials we do that the limit of hour. So, the entire plus also we have to calculate
I still put Marco in the house.
all right.
And this is the pumps up pumps and they just it up and define that.
And that's the aspect. What's your experience?
I think one of my books.
The hydrolysis is a very interesting topic. So even in the hydro engineering in Melbourne, they also have a laser cleaning system now, because even they see in the images maybe replaced in the future. Yeah, I think you can grab maybe Thomas and me later over a beer and to ask him maybe more questions. And now I would like to introduce Dr. Paul Colegrove. Paul is engineering manager at AML 3D, again an SME that is just down the road here in Elizabeth. It's a startup company established to commercialize wire additive manufacturing, has an additive manufacturing process for the cost-effective production of large, high-performance metal components and structures. Thank you, Paul.
Thank you very much. So just a bit of background. I grew up in Adelaide and then went to the UK to do a PhD and then married and stayed there for almost 18 years. Most of the time I worked at Cranford University and they specialised in wire manufacturing. Years ago, I came back to Australia for personal reasons and started Colin. It's a startup. It was started up by Tom Student. Okay, so the company was founded by Andy Sales, based in Adelaide. One thing that's not on this slide, about a year ago, we got this good team. And about 5 years, about 50 people. That's quite a year of change. We have another presentations that the also so, basis of the process is MIG welding. So there are a lot of additive techniques out there. Probably the majority of them use powders. But in recent years, and there are a lot of advantages. There is an existing supply chain basically for welding, which we can use, and the fuel itself tends to be relatively cheap. Thomas shaking his head. We can debate that. The main business drivers are, first of all, you can produce a part with less material, and particularly if you're starting with a solid block of material and then you're machining that to a final part shape, if you can reduce that material quantity, then that can often lead to a significant cost saving. And where the material is particularly expensive, you think of titanium, for example, there is an opportunity there for some quite significant cost saving. The second one, which is often forgotten, is the reduction in lead time. So with a lot of large engineering parts, you want to get it made, you need to 4 things to make it, and before you know it, the lead time might be 6 to 12 months. Whereas with our process, once you've got your part shape, and then do the part planning, and that can be reduced to third one links with the first one really. If you're using less material, that can lead to a significant environmental benefit. And then the final one also leads on from using less material. Using less material, then you need to do less machining. And titanium machining in particular is quite expensive. Now the features over competing technologies. First of all, you've got quite high deposition rates with the wire additive technique. We've got relatively low capital cost of the equipment, so we're using standard welding power supplies, which are cheaper than a laser-based system. A wide range of metals can be deposited, so basically anything that you can weld. Okay, if you've got a welding wire out there, we can then produce a part with that welding wire. In terms of the bead size of the deposit, we have got down to about 2 millimeters thick, but that really is a very narrow end. Normally, we're around 10 millimeters wide. The second to last point there is an interesting one with a lot of, you know, a little bit about TIG or plasma welding. You have an external wire. So with the MIG process, which is the one that we use, the wire is coaxial to the torch, and when it comes to making a part, that makes it a lot easier because you don't have to worry about rotating this external wire feed around the torch. And then the final one is that the process is quite tolerant to height variation. This is a huge advantage because as you build your part, ultimately, or inevitably, you won't end up with a uniform layout height. And if you've got a process that's fairly tolerant to that non-uniform layout height, it means that you can keep on processing without having process issues. In terms of deposition rates, these are our typical values. So for a lot of materials, it's interesting, even though you've got different compositions, but most steels are around 5 kilograms per hour, Invar is about 5, titanium's a bit less, and of course the density of titanium is less, so that ends up giving you a slightly lower deposition rate. And likewise with aluminium, quite low density, so therefore the deposition rate is lower. That of course doesn't include the utilization rate, so that's how much time the arc is on compared to the total time. And so when you're looking at maximising the productivity of the process, you really need to look at maximising the utilization as well as the deposition rate. I'll just touch a little bit on the MIG process. I don't want to go over something too basic. You have a wire that's coaxial to the torch, You then have an arc created between the end of that wire and the substrate material. And then there are a number of different ways of transferring that molten metal into a molten pool, which we'll discuss in the next slides. There are three main variants that we use. We use Fronius power supplies, so they were a power supply manufacturer based in Austria. They have CNT, CNT mix, and then PMC. And we mainly use the CNT process. So you have a torch. On the left-hand side there, you've got an arc created between the end of the wire and the substrate. Now, the unique aspect of the CNT is that the wire, rather than being constantly fed into the molten pool, pulses backwards and forwards. And so you have the arc that's created, that wire is then thrust into the molten pool, okay, and that molten material is then deposited by surface tension, and then that wire is then retracted backwards. Quite unusual. Most welding processes, that's just a constant wire feed. So when the wire is retracted backwards, you then recreate the arc, and then the whole process is repeated. On this next slide, we have an example of what's called the CNC mix process. So rather than going through all three, so this is standard. What's happening there is standard pulse welding. So you're getting a pulse of current. With each pulse of current, you get a droplet. Now it's doing the CNC. So you can see the wire going backwards and forwards, and the arc is created as the wire travels backwards. So the heat input with CNC is considerably lower than the pulse process. And that's an advantage when you come to these things by additive manufacturing, because one of the problems that you have is too much heat. So by using CNC, you can then minimize the heat into the process. So to assume at the top there, have we used or have we produced something in this particular material form? If the answer is yes, then the next step is to create a preform. Okay, so a lot of people don't realise is that the parts that we produce usually still need machining. And so if they need machining, you have to have some kind of allowance on the surfaces to accommodate that. So the next step is to create a preform. Once you've done that, we have our own in-house software that generates the parts, to produce the parts. Following on from there, we then have our own special software that runs the robot. And this is probably key to what we do is the software that runs the robot that then is able to produce the part without any problems or defects. Then have part inspection, and then finally machine. Now, these are the main list of materials that we have produced parts with. So you've got a whole range of aluminiums on the left, titanium alloys, both grade 5 and grade 23. The difference there is one has low oxygen and one doesn't. We've got a whole range of nickel alloys, and then the last column is steel. So we can, of course, there are more materials out there, and it's just a matter of getting time to investigate new material. But generally, with the process that we use, it doesn't take long for us to develop parameters for a new material. So we can quite easily produce a part in any material that you want. We can also do, and I'll touch this on this toward the end, we can look at functionally graded. When you've got more organized materials. And this is very useful for optimizing the properties in different areas. I'll just touch a little bit on materials and metallurgy. So the cooling rate is crucial to your product. And in general, doesn't happen with all materials, but in general, faster cooling rate gives you a more refined microstructure, and then that translates to a higher strength. The cooling rate depends on two key things. First of all, it depends on the part geometry, and there isn't really much you can do about that. The part shape and the distribution. Second thing, though, is the interpass temperature, and this is anyone who's done welding. Whenever you do a weld procedure for welding, you'll often specify the interpass temperature. And so if you specify a lower interpass temperature, that gives you the opportunity to get higher strength. And we monitor this interpass temperature. We can do it one of two ways. We can use a thermal camera, but we've actually found that a pyrometer is a much simpler method to monitor this interpass temperature, because you can point the pyrometer just above the area of the part if you want to deposit it. Whereas if you've got a thermal camera, you've got this great big object that you're trying to control the temperature with. It becomes very, very complicated working out whether or not you can deposit it through any different. We also then need to, if you're trying to control the interpass temperature, you then need to think, well, if you're waiting a long time for it to cool to a certain temperature, you then need to look at ways to efficiently cool the part. And so we can do that with a blower. It's very, very safe. We don't use a normal compressor, so we don't have oil in the air. We just use we basically use a big fan that's got low pressure but high velocity. We also, when we build our parts, we need to consider the height, and to keep track of that. So we have a laser sensor that does that, and that is attached to the welding tool. And we now have a video that illustrates very carefully. Yes, music in the background. So you can see the welding torch depositing material. Heat being deposited. I think then you've got the laser measurement. One of the consequences of all our funding is we've now got a slick as well as the robot, we also have a positioner, and this is the positioner that we have. It's a 2-axis positioner from ABB, and this gives you a lot more flexibility when you start to produce parts. So we have 4 main categories of parts that we can produce. So the first one is 2.5D prismatic. So this is probably what most of you will think of when you think of additive manufacture. You just take an object, you do all these vertical slices through the height, and then you manufacture your part. And that works, but it doesn't work for all parts. And you can often be quite limited in the kind of shapes that you can deposit. The next one is revolutional, and that is for parts that are rotationally symmetric or almost rotationally symmetric. The third one is radial, so that's best thing to think of there is something like a turbine blade. And then finally, a pipe shape, which you can see on the far right in that square. So 2.5D, so this the object that's shown there, as I said, slicing, and you often then also need to think about this object here has got stiffness, and you need to work out how to do the intersection to the main body. Changes. See that is it in this case with that result. And then the next main category of parts is revolution. Now the thing is, if you did that slicing in slices, you've got this big overhang particularly at the bottom. So you can use your position to get effects. So you have 2 axes there. So So first axis, when you start, is at 90 degrees, and you start depositing on a cylinder. And then as it builds up, axis 1 moves downwards, and then on the halfway point, it's here axis 1 is 0. And I forgot to mention that axis 2 is continually spinning around. So it's a little bit like a Collis wheel, where you've got the object spinning, and then you're depositing material as you go along. Apart from that, say you cannot deposit once you spin air. Now this Panama chop is actually done by that method. So all that. Right, so pellets, so the slice of this case is on the surface, with a cylindrical surface, and once again we're using our position one tray, and then rotate. Apart from the machine that developed, also do 5 Colgroves and the layer thickness, you see the layers go around the pipe, and the layer thickness is uniform. One of the key things for getting the process to work is that you have this problem with layer height control. So when you start manufacturing parts of example, you end up with a very low heat sink, and so your bead shape changes completely. Okay? So it ends up being much narrower and much higher. And so if you didn't do anything, what you'd end up with is a massive hump in the middle, and everything around it is much lower. And so from the key bits to the technology that we've developed is to get around that problem. So just some limitations of the geometry. You want to start with the substrate. It's usually the same material type. Can't possibly clear. Ideally, you deposit a flat position, although it can do positional deposition as well. And the robot positioner is used to do effect to this is an example of dissimilar deposition. So we've deposited titanium onto niobium. The niobium in this case was only 1 millimeter thick, so it's super thin. And so it was quite a challenge to not blast the material away, for want of a better term. So we used this process called cycle step, which is developed by Fronius. So it should be quite obvious how it works with this video. In niobium in the box, and you can see that we've got a few boxes that then cools down, and we've got a few more boxes, and then that just needs to go. Also to note is that titanium it oxidizes very quickly, and as a consequence of that, you need to shield the environment, otherwise it gets very quickly. We do that with we developed in the UK, and this is our current incarnation of it. Right, this is pretty much it. So we now have our filling machines. Video of it. It's still like a robot, you'll run the power supply. All our software. Speakers, you've got capacity machine, storage.
During the present technology we is developing right here in Adelaide, South Australia. I start with a question. This parking system, how so you can really just upload the CAD drawings, push a button, and then you have to wait parking coming out.
It's you know it's we're not quite at the stage where you can just. There is and that takes time. And then once you have your parts, then you do load those into the machine, and then you can manufacture your part. So there are a lot of stages in between, but it is sort of they are the main steps to manufacturing your component. But we do, you know, before you start manufacturing a part, you've got a lot of things to check. For example, collisions with various different things. But it's like anything, you know, you're going to have challenges to overcome. But as long as you're careful, then you can manufacture your part.
Oh, that's really cool. What about inspection or quality inspection after it's done? Do you need to do any sort of non-destructive testing, or how do you guarantee quality of this?
At the moment, we're predominantly looking at that after the parts being manufactured. Before that, the UK particular area, and people were looking at doing that. You can detect the defect while you're building it, and you potentially grind or machine it back, and then you don't produce the whole thing with the defect in it. So there are a lot of advantages to that, but of course, there are also a lot of challenges because you know the techniques that typically are used for ultrasonic methods, they generally like a nice flat, clean surface, and we don't produce a nice flat.
regarding the mechanical properties of those.
Yeah, I think in most cases we can get through. It's a bit of a challenging question because sometimes you've got a correct comparison. So price export is a classic. You've got price export wire and you've got price export wall. It's basically the same thing. I mean, you can basically the same studio. Steels are a bit different. So you've got a whole range of steels, and then you've got a whole range of welding wires through. So it's a bit hard to sometimes it's even better than raw material, but yeah, it's generally around the raw properties. But you do need to look at it on a case by case basis.
What's the duty cycle on a machine like that?
That's basically the same as utilization. The utilization, yeah, you've got the duty cycle on the welder. So you can look at the nameplate of the welder, gives you different duty cycles for different currents. So with lower current values, you can feel that 100% fine. We use sort of, we've got a 500 amp power supply, and I can't remember the exact values, but as you approach that 500 amps, then you'll have to in addition to that, in any case with our process, we're never leaving the arc on all the time for electrical reasons. The right measurements for building.
Have you used cord wires? Have you been able to use cord wire project components?
Like a
Ceramic field wire?
we haven't done that yet. As I said, anything where there's a welding wire, you've got that in some of the hard, I should qualify that with the hard facing alloys. Some of them you deposit and then they crack. They crack. But in most cases, there's a welding wire, then
Just make a part, yeah, then send it over to data board, yeah, it's 50 kilometers, a few kilometers and we're apart from each other. Are there any more questions for Sure.
I'm curious about if you're able to make companies such as localities in parts, particularly if you could do it with the one. Yes, you can produce parts from localities. We have done it with actual assembly, something that's done in the recent and yeah, so as you produce your parts, you put the material and close up the body. Probably difficult to get something that's perfectly circular, which is maybe what you want. You could certainly get more of a triangular shape relatively easily. And yes, you could have cooling channels in your part, for example, which could be quite useful if you wanted to produce a die of some kind. So you've got a lot of new capabilities there with the technology. You can also use it for lightweighting, for example. So if you wanted to have some internal cavities to reduce the weight of the component, and that's something else that you can quite easily do.
Well, do you have a, obviously modular system, is there a maximum size and that's what you can do?
Well, we can ask this question so within reason, if the length of the thing is the length of the track. Okay, so if you have a 30-meter long track, you can produce a 30-meter long part. We haven't done it, but there's no reason why you couldn't. Yeah, and then if you have another track, then open the door to that. But of course, you've got the robot working with. So you get ADV produced with the art. Robots at the moment, and they will have certain reach. So if you just have the track in one direction and then a particular ADV robot, then in the Y direction, like the reach will be whatever that robot is in the Y direction.
Okay, then thanks for getting here. Colin is setting up his mic. Just a few words about Colin. First of all, Colin is my boss, so I can't say anything bad. Yeah. Colin is the first industry associate professor here at the University of South Australia. Again, he's not just as Peter said at the very beginning, here at the Future Industries Institute, we really embrace the research that is inspired by industry. We really want to do applied research and not ivory tower research that just simply ends up in fancy publications that nobody needs.
Thanks, Christy. I'll try and bring it home, keep things a little bit lively for you in the last 20 minutes, 25 minutes, maybe a bit quicker, or else I'm not going to. Cool. Okay. So, surface finishing. So, Thomas and Paul have done an awesome job making the part, but it's an additively manufactured part. It's not in the shape or the surface finish that we require. Therefore, we enter this surface finishing, and that's going to be what my topic is talking about. So, I'll talk about myself a little bit. Why do we care about surface finish? Some options available. Just go through a list of them, and then I'll do a case study that's on a project that we're working on right now. Really interesting for space-based application. So, my background, applied physics as an undergraduate. I went and worked for Solar Optical, which was the second largest ophthalmic manufacturer in the world for a while. I did R&D there. Did a lot of coatings work, so that's my background with coatings. I came to the university back in 2004, so I've been here 17 years, and during that time I've done my PhD in material science. Some of the projects that I'm working on right now, obviously really good collaboration with LaserBond in the mineral and mining sector. It's hardware resistant coatings, but also a little bit of work in medical. That's more the material science about medical, quantifying material properties for medical devices and the space one I'll talk about later, so I won't go through there. Automotive, for the 17 years I've done automotive-based research, and they're decorative functional coatings for the industry. And that one's gone back in 2011, a mirror lens production with our industry partner at Samar. That ended up to winning me the prize, Prime Minister's prize for new innovators. And we've since then tweaked that product into decorative coatings, and they're being made here in South Australia and exported to certain supercars in Europe. So again, it's showing that UNISA partners with industry here in South Australia to develop new technology that's world class. So surface finishing of AM, I'm going to talk plastics and metals here because they're both relevant. The part that you get out of it is just too rough. It's not the shape that you want. It's not the surface finish you want. If it's plastic, it's normally a filament, and then that filament has steps. If it's selected laser metal, then you've got the particles and layer by layer again in there. If it's lamp, you've got larger layer by layer section. If it's LND laser, it's finer, but they're there. And you saw in our Industry 4.0 lab, the binder jet, even that has layer by layer surface finish. So we need to get rid of it. How can we do that? Why do we want to do it? Obviously, aesthetics. A lot of the time, we want the part to look nice, so we want to do post-processing. By doing surface finishing, you'll create an isotropic, even, uniform surface. That could be good for some situations. By creating a smooth surface, getting away from undulations, pitting, maybe even surface cracks, will increase its fatigue and crack resistance. Some of the post-processing options there will increase the part's corrosion resistance. And as Paul said, for ultrasonic detection of defects, you want a nice smooth surface, so that, as well as we can add function. So there's lots of reasons why we need to do it. How can we do it? Lots of options for there's lots. Number one is print strategy. How do you go about doing it and largely affect the inputs of the surface finish that you end up with? I've got two examples there of optimizing the print strategy of the part. Again, I apologise for this is an LFV part made without optimization. If you don't put the powder in the right place at the right time, you end up with a very rough surface. That's the simple one. Then you've got mechanical techniques, electrical techniques, and then a few others down the bottom. I think all of these, most of you would have been familiar with some shape or form. Vapor polishing, I'll go through them. But there's lots there. My favourite is coating at the bottom, but that's my expertise. Okay, so let's do this electric discharge machine. So this is good for metal parts. You can use a wire, you can use a tip, you can use a die. EDM is really good for very hard materials. So for surface finishing hard materials, it's an option. The trick is they have to be conductive. You just need to know that one of the operating costs is the tool. But at the end of this section, I'll give a bit of a summary of comparison of the surface roughness that we achieve. We can get pretty good finish with EDM. Laser polishing. So if Thomas has made a part, he's got it sitting there on the table, he's got a laser, he can turn the powder feed off and then run the laser over the part to smooth it off. That could be a really good option for you. You're already melting it. It may have some sort of other effects on the surface finish or the surface microstructure, but it's another option available to us. Again, you're remelting it, so you can create a heating and cooling cycle. You can lead to hardness improvements. However, one drawback is, I guess, it's a welding process. You may have some sort of waviness occurring. So you might get short range roughness improvement, but your long range roughness may still be set. Typically done for metals, but I do know that the Fraunhofer has been doing laser melting of plastics to create smooth surfaces. So that's what interests me. Some really old school classic ones, vibration polishing, get a medium, throw your parts in, vibrate it like crazy, simple, effective, very good for fragile parts, very good for plastics and metals. You can change the surface finish by selecting the right medium, how big it is, how hard it is, the organic medium, very fine polishing. Shot peening ball burnishing. I saw Mohammed here, this is for you, Mohammed, he does some research on ball burnishing. They've got a PhD student doing combined shot peening and ball burnishing surface improvement. These are going to surface finish. Shot peening will definitely harden the surface and get an improvement in surface roughness, but maybe not enough. Ball burnishing, that's a technique where you're rolling the ball under the force across your path, plastically working that surface, and that will end up smoothing and also hardening at the same time. Both of these processes are only going to be useful for metals. Okay, single point diamond turning. So now we're getting into very fine machining that can bring about a very low surface roughness and near optical finish. Diamond chip is selected, machined with the right crystal orientation to make it hard wearing and self and will hold its shape during machining, and then you can get very fine surface finish with it. Good for metals and plastics. There are some limitations. Anything containing carbon will end up reacting with your carbon tip and basically you choose through diamond tips like that. Electro polishing. So most metals can be electro polished, nice and simple. Hook it up to a power supply, don't reveal a liquid off your road. Can create nice smooth surfaces. And there are refinements to that where you can do this dry electro polishing basically with a conductive medium. You drag your part through this hard particulate conductive medium. So you've got abrasion, but then on impingement you've got a electric discharge. So you've got both electrical discharge machining as well as mechanical wear going on. And that combined can create a very smooth surface. It's the refinement of electro polishing. And good old grind and polish. So any metallurgist will tell you to get a nice metallographic sample, you grind it and you polish it. Options for your grinding is a two-body wear process, a little bit harsher, and give you micron style roughness. Go on to a polish, which is a three-body abrasive process, a little bit more gentle, going in successive fine polishes with your mirror finish. Good for both metals and plastics, complex shapes, and which are doable. So these glasses were made with grinding and polishing. So if you're wearing glasses, the back, most likely the back surface has been ground and polished. And there goes my solder. Okay. A brief comparison of the typical sort of surface roughness that you're going to be expecting. So the very best, you're in that grinding, polishing, coating I'll get to in a second as part of the case study. Diamond point turning, it's in the nanometers of roughness. So the scale there's microns, those ones are in the nanometer of roughness. Then you start getting worse and worse as you go. It's fit, you choose a surface finishing that's fit for purpose. So if you're doing a hydraulic rod, trying to get rid of hexavalent chrome and putting down the laser plating and then doing super finishing, that might be enough. You don't want to add cost that you don't need to. But if you're making an optical surface that you want to mirror coat, then you're going to need to go down to the diamond point turning or coating. So case study, where are we applying this know-how and why would we want to? So project with Camille Zuber, a researcher here, a few other people in here, are working on freeform optics for space-based applications. So these are complex shaped mirrors that go into sensors on satellites, and they'll be used for imaging, either imaging the satellite or imaging the Earth as it passes over. Obviously, it's going to be a complex shape. We want it lightweight. We need to pick the right materials so that it will burn out on re-entry. Needs to be an optical finish. We have to be very dimensionally accurate, both at the small scale and on the large scale. We don't want roughness, because that will lead, or small scale roughness will lead to scattering of the light. Large scale will lead to distortion of the image. And it's small in numbers, so low volume, one-off parts. So it really leads itself for additive manufacture. So can we additively manufacture this part? And can we do it to the right size? What materials should we use? Can we do it out of metal? Can we additively manufacture a plastic part and still get to parts? These are the sort of questions that we're asking in this project. So there are space-grade plastics. We can print them in the industry 4.0 lab in school. So that's what we've started to do. Jevon is still here. Yes, you see, Jevon is the postdoc working on this process. So anything that I say here, he's what he's done, and I'll just make him credit. So yeah, these space-grade plastics, low-out gassing. For a plastic, they have low coefficient thermal expansion sensitivity, and we need to work out what sort of dimensional tolerance we can get. Metals, there's metals out there that you can 3D print and get the right sort of tolerance with. This project is going to be looking at alternative metal alloys that are made for extra give extra either value or extra performance. And then we need to work out how to machine them. So that's the project's aim, is to explore what options are there and then work out what's feasible. Getting onto the plastic stuff. So this is space grade plastic, 2 different grades of it. As printed, it's filament type printing. You end up with very porous open structure. If you try and grind and polish that, you'll end up just exposing more and more holes of the porosity. So Jevon worked up an annealing or a fusing process and it's a solid object. And the approach that we've taken just now is grind and polish. Next on our list is to try the single point bond alternative. And that's happening. But surface roughness, talking about what we can achieve. So just grinding it, we're at the 0.3 microns, but once we get to our polish, we're into the 9 nanometers. On the small scale, that's good enough for us, but you can see up there we've still got some large structures in the polish, which isn't quite acceptable. Like I said, we had to fuse the plastics together. That plastic there fused really nicely. This one here didn't fuse completely. You can still see the porosities running down. So no matter how much we ground, how much we polished, which kept exposing these porosities. So this plastic we could get to fit wasn't fit for purpose. So when we mirror coat it, if we put an aluminium coat direct to the surface that we've polished, we get a mirror finish, but it's cracking. So that's where the coating comes in. So the image on the right is that same part that's been polished but then overcoated as well. So in our University of SA coating system, it's a liquid plus vacuum coating process. So we put the liquid coating on, it self-levels, fills it in voids, gaps or scratches, and gives us a mirror-like finish to then put the metal down. Our coating system, like I said, we've been working with automotive for a long time. This coating system has gone into production and we've done 3 million mirrors. Well, SMR have made 3 million mirrors. They've been in service for probably 10 years now. The first mirror was made 2011 and it's been on the car for 10 years. So we've got good durability, good product data out there, so we know it's durable. For a space-based application, we're talking a very harsh environment, very harsh UV, exposure to oxygen radicals. This system puts the metal layer as the very top layer. Metals are good at resisting UV radicals as well. So we think it's going to be a stable coating in this type of environment.
Will it be a good adhesion?
Yes. Yeah. Yeah. So the coating stack is 5 layers, and each layer is picked to do a particular function. And the very first layer is this compatibility layer. So we've done it on metals, and we've done it. It was originally designed for plastics, but we tweaked it. But we think that no matter how much surface finishing you're doing, you'll probably end up using the coating system, because then you can overcome any surface imperfections, but then you pick what metal that you're going to be having as a reflective surface, and then tune the reflectivity to the properties involved. If it's an infrared sensor, you might put gold down, so you're very reflective in the infrared. If it's an optical system, you might want aluminium or silver, so you're very reflective in the visible. And that's one part of the nicety about that coating stack. I think I might skip that. So I guess this was just looking at the coefficient of thermal expansion of the plastics. There's in the standard for space grade materials, I want you to measure it in different temperature ranges, which is what the 3 graphs are. And then this is just looking at one of the directions sort of thing. This, I guess the take-home message here is that the plastics, which are the blue, orange and grey, do have a CTE, but they are acceptable we're in the range to be acceptable. So we're not going to rule them out straight away for thermal expansion just yet. Metals are obviously a lot better. The other one is outgassing. How much of these plastics going to outgas? Again, we've got this TML, which is a measure of the mass loss. If it's less than 1%, it's okay. So for those plastics that we've got there, they're okay. But if you actually look at the graph, there is the pressure rise due to the plastic being there. You can see the pressure rise up there. They do outgas, but they're acceptable. But if you look at the very bottom line, there is a green dots across the bottom, and that's what happens for the metal. So metals don't outgas, plastics do. But again, it's probably acceptable. So at this point, we can print the plastics. They're probably okay for CTE. They're probably okay for outgassing. So what's next? We need to get onto these complex shapes and use the single point on and turning. And then we're working with one of the partners, AM Aero, to look at some of their more unique metal alloys to repeat this process on. So, quick summary. Most additive manufacturing parts are going to need some sort of surface finishing. There's lots of options out there. The decision will come down to cost, time, and what you need to achieve. And I think don't be scared of just trying to go with one process if your requirements are very high. Try combining different processes and you might be able to get where you need to be. Cool. Thank you.
I'm trying to get everyone else. Do we have any questions from the audience? Mohammed has one. Yep.
Now, do you remember the question that I told you?
Colin, thank you very much for your nice talk. I think I don't have a question, but comments though. I think it's a very good talk. I mean, that you actually captured some of the aspects and approaches people have been using for surface treatment, monitoring the surface roughness, and also altering some of the mechanical properties, so which is very good thing. So, and then you have presenting that 3D printing, and then you are going to use the coding, right? Yeah. So, is it possible we can even without coding? Is it possible we can finish and get the mirror, reflective mirror, directly by the surface finish without coding?
Yeah, I think for metals, yes, there's probably is. So the guys at DSTG have used aluminium. Yeah, so they've been using aluminium because they want aluminium-like reflectivity. So they've been using aluminium and doing single point time and turning of that. Actually, you get it deforms instead of cuts, so you end up smudging the actual surface, the shape that you want, so you're getting distortion of the shape. So I think it's possible, but work needs to be done. And that's where the metal alloys might be better. If we can pick an aluminium alloy that still has a high reflectivity, but machines it better under single point time and turning, then that might be a simpler thing. And then you're cutting out that coding step, definitely. Oh, question from the audience, from the ether. Where's the camera? Up there. Right, okay.
Okay. Sam Pinches from Swinburne asks, do you need to do anything in particular to manage residual stresses for optical components?
Good question. I don't know. I think in the parts that we've processed today, up until now, we've had to do an annealing to densify them, and that's right now that's annealed out any stresses. So we haven't had to do anything special up until now. Hopefully that answers your question, Sam. And now that Chris has heard that you've asked the question, it's all good.
You can go home, Sam.
Yeah.
I have a question.
Yeah, of course, Chris.
Right.
What would be the criteria seem to be for these mirrors can disintegrate on the outfit? Please expand on that. I don't understand why you go to all of this trouble to build something. And then what's the trouble? Why?
So these are designed for CubeSats, and they're only there for small satellites in the same shape of a shoebox. And for defence, they're easily deployable. Probably only have a short service life, maybe 12 months, maybe 2 years, and then they'll deorbit. And as they come out of orbit, you want them to burn up and not land on people's heads, basically. So if you've got a lump of titanium, there's a mass limit that you can have of that titanium up there before, and then there's a mass versus melting point sort of relationship that you need to balance, sort of thing. But then some countries like China don't worry about that, and they send it, because right now I think there's a rocket thing waiting to come back, isn't it? Yeah, a few tons. So maybe we're worried about nothing. Did that answer it?
It answers it, but I don't understand.
Yeah, just I think people. Yes, sorry. Going further than your 17 years in SA, in the PhD at Polymer Institute. So when you talk about the outgassing, is that really just what polymers, plastics tend to degrade under space conditions, that is vacuum and UV. not just because they outgas and any gas in there, but it actually degrades the polymer. You can switch often enough just to the blind or to yeah. Any thoughts or investigations into that?
So in our system, we can measure the volatiles that have been lost during outgassing, but we haven't done that. So that's a good point. We should do that. And that's something, yeah, that we should follow up. I think I'll leave it there. I just want to say thank you to Christy for putting this event together. So she's done all of that. I'll pass it over to you to do the form things. But thanks, Christy. It's been really good.
Thank you, Colin. I wrote down a few things. So first of all, I want to thanks to all three speakers, maybe for the really high quality talks. And I'm not only saying that because I selected you guys to present here, but we are really thinking that were good talks that we heard here tonight. Then I want to thank you, the people maybe working in the background. Yeah, Min, Anthony, Andre, and Ting. Yeah, who did all the technical stuff in the background and also worked around that we are going to have food. And then okay for food and drinks, maybe all to our skin here. And the sponsors who paid for these drinks were Microscopy Australia, the Future Industries Institute, LaserBond, and SEAM. So thank you for that. And then I also want to mention again maybe the professional organization. So this is a joint event of Materials Australia, the Australian Corrosion Association, and Weld Australia. We have maybe people here in the audience who are members of some of these professional organizations. Some of them even have maybe several of them. If you want to become a member, talk to maybe one of us, and for students it's often very cheap, like about maybe $25 a year, and you have events like this where you get free beer. Yeah. But definitely worth the $25. Yeah, that's it. I invite all of you maybe just maybe outside maybe in the foyer where we are going to have a cold beer and a little bit of food, and then we can just maybe ask the presenters a few more questions about their talks. Thank you.